These are the examples for lesson 2.1, Patterns and Conjectures. In this video, you will learn to use inductive reasoning by discovering patterns, then taking those patterns and making a conjecture. You will also learn what a counterexample is, how to create one, and show when a conjecture is true or false. Example 1. In this example, you will learn to search for a pattern to write the conclusion to a conjecture. So here we go. The number of line segments formed by 4 points, no 3 of which are collinear, is blank. So here we have our conjecture, but no conclusion to it yet. They want us to find the conclusion. First thing we do, we have we want to figure out how many number of lines there are formed by 4 points, but the 4 points, 3 of them cannot be collinear, or 3 of them can be collinear. So start with 1 point, draw another point. No 3 can be collinear, so that means the third one can't line up with these two, so I'll put it right about here, I suppose. And then we need a 4th point that's not collinear with any 2 of the other 3. So, like, we couldn't put it here because that would be 3 collinear points. We couldn't put it here, that's 3 collinear points. So I'll put mine right about here. Then, to figure out the answer to this, or the conclusion to the conjecture, we figure out how many line segments are formed by these 4 points. From one point to another, remember the postulate that says between any 2 points exists exactly one line, or one line segment. So there's one, there's another, here's a third, here's another segment between 2 points, there's another segment between 2 points right here, and one more between those 2 points. So we count those line segments up and we have our answer. 1, 2, 3, 4, 5, 6. So the answer is 6 line segments. Example 2. In this example, you will learn to search for a pattern to write an entire conjecture. Here we go. Given 5 collinear points, how many different ways can we connect those 5 collinear points? Now remember, the key word in remembering what a conjecture is the word pattern. You're always looking for patterns. So we've got a chart here, or table, with number of points. So we want to make sure that we draw the number of points under picture here. There's 1 point here, there's 2, we need to make sure they're collinear. Of course, 2 points are always collinear. 3 points need to be collinear. 4 points need to be collinear. And 5 points need to be collinear. And we need the number of connections between any of those 2 points, or any 2 points. So be very careful when you read a conjecture to make sure you're following it correctly. Well, here there's only 1 point, so there are no connections because there's no other point to connect with. So this is 0. And then here we've got 1 connection between the 2 points. Here we have 1 connection between 2 points, another connection between 2 points, and then we have a 3rd connection between 2 points. Remember, it didn't say a line segment or a line, it just said a connection. So that's 1, 2, 3 connections. Here we have 1 connection, 2 connections, 3 connections, 4 connections, 5 connections, 6 connections, and we already have a connection between these last 2. So that's 6 connections. The last one, and this will be our conclusion, by the way, there's 5 collinear points. There's 1 connection, 2, 3, 4, 5, 6, 7. Go to the second point. 8, already have that one, 9, and then starting from here, the only connection left is between the third and the fifth, 10. So the answer to this is 10 connections. Example 3. In this example, you will find and use a pattern to predict a result or results. You probably remember doing a little bit of this in Algebra 1, at least this part of it. Has two parts, A and B. Part A, 3, 9, 27, 81, and so forth. Now remember, a sequence is a literal mathematical term. A sequence usually contains numbers, but it doesn't have to. Is a list of numbers, things, objects that have some sort of pattern between one and the next, and so forth. So what you need to always do is start off by always looking for all possible patterns, then eliminate any patterns that don't work through the entire sequence. So one thing we could do between these two is take 3 and multiply it with 3 to get 9. But another thing we could do is we could add 6 to 3 and get 9. When we come from 9 to 27, we notice that adding 6 to 9 doesn't give us 27, so adding 6 doesn't work. But multiplying by 3 does still work. And then make sure you check all terms in the sequence that you're given. 27 times 3 is 81. So, pattern, we're asked for the pattern. You multiply each term by 3. And they ask for the next term. And the next term would be 81 times 3. When we multiply 81 times 3, we get 243. So there's our next term, and there's our pattern. Our pattern is written out using language. B. In B, we've got a sequence of polygons that are inscribed inside the same circle each time. And they're wanting to know the next term. Well, our first term is here, second term, third term. Notice that the circle stays the same each time. So the pattern is something like this. Each term repeats a congruent circle. That's the symbol for circle. And each term, and you'll notice each term, the polygon has one more side to it, one more side. So we can say this is a triangle, this is a quadrilateral, and a pentagon. So each term adds one more side to previous polygon. And so our next term, we add one more side to the previous term, which is the pentagon. So we draw a circle about the same size, and then we draw 6-sided polygon, which is a hexagon. 1, 2, 3, 4, 5, 6. And so this is our next term, and this is our pattern. Example 4. Well, in example 4, it's going to be a lot like example 3. But you'll also identify the previous information and conclusion to the conjecture. So, it says look for a pattern, look for and state a pattern. What is the next term in each sequence? Circle the prior experience or known information, and box in the conjecture in each. So we have two parts. This is the first one here. We have 1, 1/3, 1/9, 1/27, and so forth. So we take the first term and we decide what can be done to this to give us the next term. One thing we can do is we can subtract from 1 2/3, and that gives us 1/3. Another thing we can do is we can take 1 and multiply it by 1/3, and it'll give us 1/3. Then when we go from 1/3 to 1/9 and we try to use subtracting 2/3, we discover that 1/3 minus 2/3, the pattern that we discussed, does not give us 1/9. It actually will give us, let's see, negative 1/3. So that's not the next term. So subtracting 2/3 does not work. However, going from 1/3 to 1/9, we can multiply by 1/3 again, like we did the first time, and we get 1/9. So it looks like this may be our pattern. Multiplying by 1/3. Multiply 1/9 by 1/3 again, and we do get 1/27. So the pattern is multiply each term by 1/3. The next term, we take the previous term, which is now 1/27, and we use the pattern. Multiply by 1/3. When we multiply by 1/3, 1 times 1 is 1, and 27 times 3 is 81. So we get 1/81. 1/81 is the conclusion to the conjecture. So we box it in. We circle the previous information, which was all of this. Part B. In Part B, we have an array of dots positioned in a square formation each time, with the exception of the first one. When a diagram indicates some sort of square formation, we can always investigate using a pattern of numerically squaring a number. So let's take, here we don't really have a number of rows and columns unless we say that we have one row and one column. So here we've got 1 dot, and we square it. Well, when we square 1, we get 1. Here we've got 2 rows and 2 columns, or 4 dots. So this is really 2 rows and 2 columns, a square, and we square it and get 4. And that makes sense because we have 4 dots. And here we have 3. We square it, we have 3 rows and 3 columns, and we get 9, which means 9 dots. And so forth. So the pattern is add 1 more to the column and row to the previous term. That's what we're doing each time. Mathematically, we're just squaring each number of rows and columns. So our next term, we would take and make 4 rows and 4 columns of dots. And so this right here would be boxed in, and our previous information or prior knowledge would be what we were given. Example 5. In this example, you will learn to test a given conjecture. Test the following conjecture given the provided steps. The sum of 2 odd numbers is always even. We want to test this to see if it's true. First thing we want to do is test the conjecture using several number sentences. So what we do is, and there's a lot of vocabulary involved in a lot of this testing of conjectures, a lot of number sense also. The sum means we add of two odd numbers. You have to know, of course, what odd numbers are. And our answer should always give us an even number. So let's come up with some examples for tests. How about the sum of two odd numbers? How about 1 and 5? Those are both odd. We add them together, we get 6. Is 6 even? It sure is. You generally want to come up with 3 or 4, probably 4, and sometimes more if you're having difficulty establishing your pattern. So let's do another one. How about 3 is odd plus 9 is odd, and we get 12 when we add those together, and that's also even. Another one, how about 7 plus 11? Those are both odd. That gives us 18, which is even, so it's definitely looking like we're establishing a pattern that this is true. Let's take one that's out of the norm here. 635, that's odd, plus 251, that's odd. Add these together, 5 plus 1, that's 6, that's 8, and 8. So 886 is even. Once you've established that, you can state the conjecture as being true or false based on this test. Well, obviously it works for everyone we tried, so we would say conjecture is true. Example 6. Similar to example 5, test the following conjecture given the provided steps. The sum of two numbers is always greater than the larger number. It's a little different. The sum of two numbers is always greater than the larger number. In other words, the larger of the two numbers that you added together. So for instance, this says test the conjecture using several number sentences that show it might be true. I'm going to start off with the first one, the most important one. 3 plus 4, that's any two numbers, 3 and 4. Add them together, we get 7. So the sum of two numbers, they're saying that the answer is always 7. The answer, the sum, is always greater than the larger of the two numbers we added together. The larger number is 4. So is this true? Yes, it's true. So larger of 3 and 4. And you might want to come up with a couple of others. 2 plus 1 equals 3. So 3, the sum, is greater than the larger of these two numbers, 2. And how about one more? 5 plus 10 equals 15. So the answer, the sum 15, is greater than the larger of the two, 10. So all of those work. However, if possible, provide exactly one counterexample to show the conjecture is false. Remember, a counterexample, all you need is one example showing this is not true to make this a false conjecture. Just one specific example. So how about if we use negative numbers? Negative 2 plus, how about negative 3? Well, negative 2 plus negative 3 is negative 5. And according to our conjecture, negative 5 should be greater than the larger of these two numbers added together. Well, the larger one is negative 2. It's closer to 0 in the number line. Well, is negative 5 larger than negative 2? No, it's not. So I'll put a slash through that. And this right here is a counterexample showing that this conjecture is a false conjecture. Example 7. In example 7, you will test a conjecture that involves geometric concepts that you've already learned in previous lessons. So here we're given that line segment AB is congruent to line segment BC. The conjecture is B is the midpoint, or must be the midpoint, of segment AC. Now that seems rational. It seems like it would make sense, but what we need to always do first is start off by making a diagram and labeling it of the given information. So here we're going to take AB. We've got AB is congruent to BC. Well, here is an example. If I call this point A and this point C, exactly halfway between, tick marks there, this right here definitely shows us the given information. AB is congruent to BC. And the conjecture is true here. B is the midpoint of segment AC because it's exactly halfway, or it divides AC into two congruent parts. But then you need to see if there's a way you can use the given information where the conjecture does not work. Do you think that's possible? Watch this. Here's A. Here's C. Here's B. AB is congruent to BC, but B is not the midpoint of segment AC because segment AC is right here. B is nowhere on that segment. So this would be a counterexample right here. Therefore, this conjecture is false. Counterexample. Example 8. In example 8, you'll find and state a counterexample to a conjecture. It says, find the counterexample that disproves the following conjecture. Here's the conjecture. Supplementary angles are always adjacent, like this one. So they give us an actual example here of how this could work. These are supplementary angles because their measures add to 180. 100 plus 80 is 180. And they're adjacent to each other because they share the same ray and they don't overlap. So this is an example of how this could work. So to come up with a counterexample, we need to figure out a way we can have supplementary angles, this first part right here, but yet they're not adjacent. Is that possible? It is if you do this. Draw an angle that measures 100 degrees and another angle that measures 80 degrees, but that are not adjacent. In other words, they don't share the same side. So this would be a counterexample to that conjecture, making this a false conjecture. Finally, example 9. In this example, you again will test a conjecture that involves geometric concepts. We want to test this conjecture. We're given that points A, B, and C are collinear. And we want to look at the conjecture AB, the length of AB plus the length of BC equals the length of AC. Well, that seems like it might work. Let's see if that works. If we put point A here, and put point B here, and C, they all have to be collinear, so let me line these up. Let's put C way over here. These are collinear because they all form a line here. Then the length of AB plus the length of BC equals the length of AC. So it works with this particular example. But before you say it's true, we need to see if we can come up with a counterexample to show that it's false. Now, if we can't come up with one, then it's true. But if we can come up with a counterexample, then we have to say this conjecture is false. So, is there a way to do that? Is it possible? Watch this. Here's A. Except this time, let's move C here and move B here. Are they still collinear? Yes. So the given is there. It's true. It has to be true. However, this sentence now doesn't make any sense. The length of AB, the whole thing, plus the length of BC, which is this part right here, equals AC. That doesn't make any sense. This is a lot shorter than either one of them. So AB plus BC does not equal AC here, and this would be a counterexample. This is a false conjecture.